Okay, in this video is where we really get into what you actually physically will do to design a beam. And we talked about in the previous videos that we need to check 3 things total. We need to check for moment, shear, and deflection. So first we're gonna do the moment. So when you are designing a beam or choosing a beam to carry a moment, the first thing you have to do is take the maximum moment from the diagram and multiply it by a factor of safety. So hear me out. We've already looked at a beam with those arrows pointing down. Those were the forces pointing down. Then we figured out what the reactionary forces are. Then we created the shear and moment diagram, and then we calculated the maximum moment and maximum shear. You are taking the maximum moment of the moment diagram and multiplying it by a factor of safety, which is 1.67. That'll beef up that max moment, and then that beefed up max moment we call the nominal bending moment strength, or the design moment. And we will design our beam to be able to handle that beefed up moment. Again, don't be intimidated by these equations. That's why I'm not even going through them. All we're doing is saying that our beam that we're doing needs to be able to handle more than the maximum moment from the moment diagram multiplied by 1.67. We've done factors safeties before when we did stormwater management, same concept, 1.67. Once we have that gives us our nominal bending moment strength. So here is where we say that our nominal bending strength is equal to F of y times Z of x. Okay, F of y is just the yield stress of steel. We've done yield stress earlier. Yield stress is just the strength of the steel based on whichever type of material we're using. And I'll tell you that. I'll tell you it's A36 steel. A36 steel, you know, can handle 36 KSI. GR50 steel can handle 50. Certain types of wood can handle 1900. Actually, even less, or 1.9, I mean, sorry. So then what is this Z of x? Z of x is actually what we are ultimately trying to get in order to choose the member we need. Z of x is called plastic section modulus. Now, where do we hear plastic earlier in this lesson? That was when we were talking about the regions. Remember the stress and strain graphs we did earlier in mechanics and materials? This is where that comes into play. Whenever we had a stress applied to our beam, which was greater than the yield stress, we were in the plastic region, and that was bad. Whenever we had an applied stress that was less than the yield stress, that was the elastic region. That's good. Remember, elastic region is anything yet less than the yield stress. And when you load a beam less than the yield stress, when you take the load off, the beam goes back to its regular size. Any stress greater than the yield stress applied to it, once you let go, there'll be a little bit of deformation. And we don't want that. We want to always be operating when we are in the elastic region. Okay, so that's a little bit of background to plastic section modulus, but let's talk about what it actually means. So the plastic section modulus is a property of these beams right here. I'm assuming at this point you had already watched the other video on how to read the steel beams, but we're going to go through that again also. So section modulus is this is an important bullet right here, the moment carrying capacity of a member based on the shape. Based on the shape. So each of these is a different I-beam that you could choose. The plastic section modulus is right here. So you just calculated the plastic section modulus over here. Remember, we got our M of n, we divided by our F of y, and we get our Z of x. Z of x is kind of like our final answer. And once you have your final answer, you then choose the member that is satisfying that Z of x. So you would choose a member that has a Z of x just greater than the Z of x you calculated over here. Does that make sense? So let's go to this website. I don't know if I can click it. I have to go out and, oh, that's not a hyperlink. Okay. Okay, so again, you should have already watched the other video, but we go to steel sections. Don't click any of the ads or little clickbait happy. And here are all your members. And if you want to get the Z of X, you got to go to properties up here and your plastic section modulus. It's all the way to the right because it's one of the most important ones. Okay. So W represents wide flange. It's the top part of it. There's where the W is. The next number represents the depth or the height of the beam. So if it says W10, it's roughly 10 inches in depth or in height. The next number represents the pounds per linear foot, meaning for each 1 foot of this beam, it weighs 33 pounds right here. This one, a W10 by 30, weighs 30 pounds per linear foot. So all of these W10s, they're all roughly the same height. However, the ones that weigh more are going to be just a little bit thicker, meaning that they weigh more. And that's what distinguishes them from one another. So when we are choosing a member, we will always select the lightest member that works. So if both a W10 by 39 and a W10 by 30 works, I'm going to choose a W10 by 30 because it weighs less. If it weighs less, that means it's less steel being used, which means it's cheaper. So we will always choose the member with the smallest second number. We will always choose the lightest member that works. Okay, so let's recap. This slide right here, highlight, star, bold, whatever. This one's the one that kind of summarizes all of it. Here are the steps. I made this as methodic as possible. How do you choose a beam? By following these 5 steps. Number 1, find the maximum moment of the beam using the equations or using the moment and shear diagrams. Once you find that max moment, multiply that max moment by 1.67 to beef it up. And we're going to call that M of N, which is the nominal bending moment or the actual moment we will be using for the design. It is a design moment. Then we will divide M of N, which we calculated in step 2, by the yield stress, F of Y, which is going to be measured in KSI typically, and will usually be 50 KSI or 36 KSI, depending on what I tell you the member is. What we are left with is called Z of X, which is the plastic modulus. Once you have the plastic section modulus, remember the plastic section modulus is the moment carrying capacity of the member independent of the material. It's just telling you that that shape I-beam can handle this much plastic section modulus. So once you go to the charts, you choose the lightest member that has a Z of X of at least what you found in step 3. So if what I found in step 3 was, 30 for my Z of X, and I will then go to the chart and I will find the lightest member which has a plastic section modulus of at least 30. If it's 31, that's good. If the chart gives me a Z of X of 29 for a specific beam, that's not good. It's at least as big as this. And once you do that, you're actually done with checking moment. Now we're going to go check shear and deflection. I'm going to stop the video here and we're going to do these one at a time. Maybe the shear and deflection we can do all in one, but I want to keep these in more digestible sections. So we will be done with here.